Thank you for inviting me. It's been a very pleasurable conference so far. It's like great weather, no rain. It's much better than Sweden. So today I came here to present some joint work that I did while I was a visiting researcher at Xanadu about like 1.5 years ago. Took a sabbatical of my PhD, so to say. Appeared like recently on the archive, and it's about single-shot measurement-based quantum error correction via fault complexes. So like, what is this fault complex thing? Well, Adam already mentioned that like, oh, it's just the code, it's not a protocol. Like, we can't really like think about what happens like in space-time. And I hope that like in the long run, like this idea of fault complexes kind of becomes like a solution to this problem. It's like fault complexes are there to like analyze fault tolerance protocols in space-time or like fault tolerance protocols in general, and not just like stop at like viewing a static QC code, but really look at like fault tolerance protocols over time in some sense. And here we replace time by measurements, by looking into the measurement-based paradigm of quantum error correction. So it's very nice that like Katie already gave like a brief introduction to that in some way. But I will do my own introduction, or rather motivation. And when I got to Xanadu, I was asking myself, how can we do like single-shot error correction in the MBQC framework of QC? And what we found as an answer was basically, well, one way we just formalize foliation, other than this kind of like physicsy description that I will briefly explain later, by using the fault complex, this like new structure that we introduced, which is actually an algebraic representation of fault-tolerant protocols, enabling us to like use the machinery of homology, which has become like the modern view of quantum error correction, you could say. And what was nice that by studying fault complexes, we also gained many insights in other things like stability experiments, something that Laura talked about yesterday, which is important for lattice surgery. And it also could like allow us to like prove, or like something like prove, that we can do single-shot lattice surgery with high-dimensional topological codes like the Tori code. Okay, how do we start from here? Well, something that hasn't come up so much actually in the conference so far is this like CSS to homology correspondence, right? We have some stabilizer code, and if it has a generating set of stabilizers that are exclusively of like X or Z type, then we call it a CSS code. And then whether it's a valid CSS code or something is defined by whether the parity check matrices commute. And this is just expressed by this like matrix type equation. This means we can measure both sets of stabilizers simultaneously. So if we have this, well, we can actually represent the CSS code as a chain complex. A chain complex is a collection of vector spaces and boundary maps. Could be of any length. For a CSS code, it will be length 2, and we can identify these boundary maps partial 2 and partial 1 with the X and Z check matrix up to transposes respectively. Usually people say, well, in this space C1, there are the qubits. And then if you go to the left-hand side, there's usually the Z checks. So it's a lower dimension than the qubit space. If you go to the right-hand side, then there's the X checks. And as it's a chain complex, you have this like composition property that if you compose two maps, they will like square to 0. And now this allows you to like identify these like boundary maps with parity check matrices, and any chain complex gives you a valid CSS code, or like any sub or length 2 subcomplex gives you a valid CSS code. Okay, what is single-shot error correction? Well, typically it's like folklore, so to say, it's like when we have like faulty measurements, so there could be flip measurements. What we should do, we should repeat stabilizer measurements like roughly on the order of the distance of the code times to make sure that we can like also protect against measurement errors. Now there's this paradigm of single-shot error correction, which is usually like paraphrased with this like single error correction property. It's like, oh, we only have to do a constant number of measurements to do fault current error correction. And I here specify a constant number of rounds over a single number of rounds, which is maybe a more common phrasing of single-shot error correction. And why I will do this, it will become apparent later. Well, the nice thing is that we can also put like single-shot error correction codes into this like property, and some of them have these meta checks when they come from like high-dimensional product codes or high-dimensional topological codes, like the Tori code, for example. So in this case, we would identify the space C2 with the qubit spaces, and then we have these spaces for the X syndrome or Z syndromes and X syndromes, and then we have these like outer spaces. and these additional boundary maps mz and mx, and these are called the meta checks. These meta checks are classical code on top of the syndrome space that allow us to correct any kind of like faulty measurements outcome that we have, and in principle we don't need to repeat the measurements over time, and we can use this like redundancy in the checks to like correct the syndromes first and then decode the errors. Measure-based quantum computing, which is like another concept that's like in the title of my talk, is like this new, or like not new paradigm, but it's a paradigm of quantum computing that proceeds via single qubit measurements on a graph state. Usually you have some graph with vertices and edges v and e. On each vertex you put a plus state, and then for each edge you apply CZ gates. This graph state will actually have stabilizer generators composed of like Pauli x's and like z's in the neighborhood of that vertex. So that's kind of like a very simple graph state. It's just a linear chain. If we put in at the beginning some state psi, you could think about it as like the plus, the t state, for example, to like go back to like Adam's talk. And then if we measure it out in the x basis, we will teleport it to like the next point. And what we will pick up is this Hadamard, as Katie mentioned, and also, depending on the measurement outcome here, we will put up a Pauli X correction. If we do it twice, so to say, we also measure this one out, well, we'll pick up another Hadamard, which makes this X to a Z gate operator, and then we pick up another X. So what happens if we walk along this line by doing measurements, we walk like a Hadamard clock, right? The Hadamards kind of, you can think about it as like discrete time steps along the circle, and measurement outcomes are like, as Katie mentioned already, like they are not deterministic. That's kind of a problem initially for QEC, but if you build faltering graph states or faltering cluster states, then there are certain products of measurements which outcomes are deterministic, and you can use them as parity checks. Deterministic, of course, only in the absence of errors. Okay, we talked about foliation, which is this like standard principle, I call it, to make a graph state or faltering graph state from any CSS code. So what do we need? We need a CSS code, have the check matrices hx and hz. And then what we want to do is we want to build graph states corresponding to like the adjacency matrices hx and hz. And then we stack them layer by layer, alternating layers, and connect corresponding variable nodes in neighboring layers. So how does it look? For this, like our famous example, it's like the 412 code, which always appears. We start by like building this graph state associated to the Z-check matrix, which has these 4 qubits, which are measured by this additional ancillar qubit in the middle. And then there's this kind of like disconnected graph for the X checks, 2 qubit Pauli measurements through an ancillar. And we continue over like multiple rounds. So now we have to follow the second rule. We have to put in CZ gates, and we have our cluster state for the 412 code. I never really liked this because it was kind of like a very physicsy way of like, oh, that's how you do it. And what I was looking for is more like an algebraic construction of how we can describe foliation. What we can also see here is that we can actually bicolor this graph. We can color some of these nodes gray and some of them red. It's a bipartite coloring. There's only like gray nodes colored to red nodes or connected to red nodes. And typically, often people call this like either primal and dual qubit or the other way around. Yes, I wanted this algebraic description of foliation, and that's what like motivated this notion of fault complexes for us. So something that we realized is that a foliated code can be described by a hypergraph product of a CSS code chain complex C. So this is like the CSS code chain complex associated to the code that we want to foliate with a repetition code chain complex. As a repetition code is a classical code, it's sufficient to have like a length 1 chain complex. And what we can do is we can take the hypergraph product or the product of these 2 chain complexes, and what comes out is another chain complex. And in this case, 2 plus 1 is equal to 3, as Hector Bombin famously noted at some point. So now we have this larger chain complex. We have 3 adjacent boundary maps. And they also have a meaning, but importantly, because they are constructed from this tensor product construction, we immediately have access to how these checks look like. So let's go through this. Well, we have this space F1, and that's actually where the primal qubits sit. You can call them primal qubits, but you can also call them primal faults, because actually that's why we call it the fault complex, because it's like kind of tracking where are the faults in this fault-tolerant protocol. There's also the dual faults, which are colored red here. So here. So what you notice in comparison to like it's kind of like standard CSS code, static chain complex formalism, is that now you have like two separated spaces. Usually you have a qubit space, and then you have syndrome spaces next to it. What you have now is like, so to say, like X errors, Z errors, and then Z syndromes and X syndromes. What you have here in the middle, this partial 2, is the bi-adjacency matrix of the graph state. So if you ask yourself, or if your experimentalist friends ask yourself, like, how do I build the graph state? You just give them this matrix, which you can construct via algebraic properties. And they were like, OK, that's the adjacency matrix of your graph state. Build it. What else do we have? Well, I already mentioned that these are like the spaces for primal detectors and dual detectors of the graph state. And if via this like construction, we already get like the detector matrix or detector check matrix for this fault-tolerant graph state. As Katie already mentioned, usually checks are not deterministic in self of the code, so we need to like look at like detectors of this fault-tolerant graph state, which will be deterministic in the absence of errors. And I think it's like a very nice thing to look at this. Like we should take a look at this detector, for example. It's composed of these 4 measurements. And I like to think about it as like the fault complex also in a phenomenological noise model. So we can also not think about measurement-based quantum computing, but rather about like the gate-based model in a phenomenological error model. And so what is this detector checking? Well, if you have phenomenological noise, there's multiple error locations. Your check in the previous round could have errored, because then you have to take the difference syndrome, right? There could have been an error on either of the 2 qubits in between the checks, or at the measurement there's an error of your ancilla. So any of these fault locations will actually like offset this detector and will like signal that there was an error if there's an odd number of errors only, of course. Well, now you have all this like nice mathematical formalism, and you want to look for the hammer that you can apply to it. So what's the homology of this fault complex? Well, typically for CSS codes, we can, for example, extract logical Z operators of this chain complex via the first homology group. So remember, first homology group of the chain complex is whatever is in the kernel of partial 1. So whatever is like commutes with the checks, for example, X checks. But it's not the image of the HC matrix, which is basically make sure it's not triggering a check, but also make sure it's not a stabilizer of the code either. In the fault complex, things get like a bit different, of course, because now there's like 2 spaces associated to like faults. So what we have is like primal logical correlations, which are in the first cohomology group of the fault complex, so similarly defined. And then, of course, there's things that like flip the correlations, which are called the logical errors, and they live in the first homology group of the fault complex. So because we have this product construction in the case of foliation, we can actually compute them very easily explicitly via the Knuth formula, and they relate back to properties of the repetition code, but also properties of the code that we use to foliate. For example, in this case, the first homology group, it's like the 0 vector in there. Then there's like a 1, and then it's an all 0 vector tensored with a logical Z operator. So this is a logical error, which is just basically the string that looks like a Z logical operator of the base code. What you also have is this correlation surface, which is like the all 1 vector, and then you multiply it or tensor it with a logical X operator. And by doing that, you will basically span a sheet in this fault-tolerant graph state. So let's look at this here. Well, all these.
Sorry, can you just repeat what's the difference between a logical correlation and a logical error?
Yeah. So like a logical correlation basically tracks whether whatever you start in at like the beginning of your protocol is still correlated with whatever you measure after some number of time steps. Like it's, for example, in like a bell pair, there's a logical correlation between like XX, right? And a logical error would be something that like along this kind of like time frame flips this logical correlation, like in some sense like anti-correlates your outcome, so to say.
So in usual RBH, the correlation is a surface and the error is a line.
Exactly, yes. It's the smaller version of it. Exactly. So like in this case, for 2-1 code, there's this like logical, one logical operator is just like length 2 here. And then what we should do by this like description, we should like tensor it together with this like all one vector. So it's like going to span like this kind of like surface in this like 3D cluster state, you could say, right? Well, and then as you already pointed out correctly, like a thing that will flip this thing is a logical error. And it should be something that's like anti-commutes with Lx, which is Lz. And then we only need like a single string. We don't want to make a surface. So it's just this thing, which could be shifted anywhere up to like stabilizer equivalence. So there's more to this homology. Namely, there's this number of primal and dual logical correlations or errors. So typically, when we think about a code, we know that there's k logical qubits inside. And this is a fixed number. There's like k z logical operators and there's k x logical operators. In this like language of fault complexes, it's not necessarily anymore true that there's an equal number of primal and dual correlations. This was something that we found interesting, but this kind of makes sense. So think about this kind of like stability or like some memory experiment. You initialize your code, so like say the service code, in the z basis, and then you measure in the end in the z basis as well. So then you will have logical correlation, hopefully, between z and z outcome at the end. But, well, the x, you never measure x, so you shouldn't have any information about like logical x correlation. On the other hand, if you initialize in the z basis and you measure at the end in the x basis, everything should be random, right? So then there should be like no correlation whatsoever. So that means that in some cases, both of these dimensions can be 0. If you have like something that's like periodic in time, they're usually the same. And if it's just a standard repetition code, one of them is 0 and the other one is not, which kind of makes sense with our physical intuition. And from these like things, you can also calculate the fault distances, right? So think about them in some sense as like the circuit distance of the protocol. And they are just like the minimum weight operator from these homology groups, which then define the distance of the protocol. Okay, so what we can also look at is generalized stability experiments. Laura talked yesterday about stability experiments as a means to like check kind of like how good can we do lattice surgery, right? It's like instead of having like in the RHC lattice, like instead of having like a sheet that's like either like this or like this, it's kind of like going with time. I will show this later on. And in our framework, these like logical correlations, time-like correlations, they appear naturally when there's redundancies in the CSS code. So if there's a CSS input code that doesn't have full rank check matrices, there's additional correlations in these cohomology and homology groups, which I feel like drawn in blue. So this H vector is going to be tensored with this identity vector, so it's going to look like a surface if it's a 3D cluster state, and then this G vector is tensored together with this like single one vector, so it's going to be like a string-like excitation, string-like error. G is going to be in the kernel of the transpose of the X matrix, and that means that it's only going to be there if HX is not going to be full rank. And similarly, H is going to be out of the code space, not code space, but like the space C0 with modding out or the quotient stuff with the image of HX. So this is kind of complicated, so let's go back to our famous example. But before that, I should mention that this is really exactly like what Craig Gidney described as stability experiments. And to make this example more explicit, we have our 412 code, but we add these two redundant checks to it. And that what we then see is that if we combine all the rows of it, it's going to be the all 0 vector. So that means like this like G vector is actually the all 1 vector itself. And H is a single one and all zeros. So this basically means, well, if there's a single error in the syndrome measurement of the service code, well, then the syndrome is not valid, right? In the service code, usually syndromes appears in pairs, so an odd number of syndromes basically indicates that there's an error somewhere in the time-like direction. That should have appeared before. Okay, so how does it look in our favorite cluster state? What you see here, change the cluster state, looking a bit different. There's these additional red points now here on these edges, which are due to the over-completeness of the HX check matrix. And we have this like time-like correlation surface now living in this layer. It could be moved to any layer. And similarly, we have these time-like logical error strings that go from the bottom to the top of the cluster state and would have pierced the surface here exactly once, indicating that the time-like logical correlation has been flipped. So what we can do is we can also, instead of just foliating like CSS codes of length 2 described by a length 2 chain complex, we can also think about what happens if we have codes with a single shot property that are described by a length 4 chain complex. Codes like this exist, for example, if you build them based on the hypergraph product code of like 4 things. It's like the 4D Tori code is a famous example, I would say. And then we take as usual, we take the hypergraph product with the repetition code. And you can do all the same math again. And then you get these detectors, and you get the adjacency matrix of the fault complex. But what is interesting now is that when you calculate how do the detectors of this cluster state look like, or of this protocol look like, they will have this additional kind of like block row. Before we just had this row, now we get this additional row, which are the meta checks of the single shot code. So in decoding single shot codes, there was a long time the question, how should you do it ideally? This meta check code has like a distance itself. It's a classical code on top of the syndrome block. So what people initially did, I guess, to my understanding, is that you do this 2-stage decoding where you get your noisy syndrome, you use the meta checks to decode your noisy syndrome. Now you have fixed your syndrome, and now you decode your code as a usual code with hoping that the syndrome is correct. A problem with that approach is that usually your meta checks don't have the same distance as your real checks of the quantum code, so that when you first decode the checks, or you first fix the checks, then you're limited by the distance of the meta checks, which then, if you do an error, then you can't even recover it anymore. So that's not great. So later on, people came up with this idea of like the single-stage decoding, where they suggested, oh, well, we should actually include this meta check matrix into the check matrix of the code, and then everything is better. And this was kind of like a heuristic developed by Oscar Higgett and Nico Breukman, who said like, oh, yeah, that seems just natural to include it. So what we find is that with our formalism, it actually drops out immediately via this algebraic construction, which we thought was very nice. So they're automatically included in the detector matrices. You don't have to think about where to put them. You should put them there, because that's what the construction kind of like tells you to do. What is nice also is now, well, we have this algebraic construction of the graph state, of the checks, so we can very easily simulate any CSS code numerically very quickly. We don't have to go through building this graph state in the simulator. So what we did, we wanted to estimate error thresholds of 3D and 4D toric codes in 2 noise models. One was this phenological Pauli noise model. That's what everybody is doing. It's a good standard to compare whether our decoding protocols are better than what the community has done before, or if they're worse for whatever reason. And then, because I was at Xanadu at the time, and they're interested in building a fault-tolerant quantum computer based on these GKP qubits, we also used the noise model, which is like basically the hardware noise model, for their architecture. So to do this, because it's a single-shot code, you have to use an overlapping window approach, where you decode over multiple rounds until like the threshold error rate saturates, and only then you can be like, okay, that is the threshold. And we used to do this, use overlapping window decoding with the BPOSD decoder, and we find that, like as I just detailed before, that the check matrix and our threshold error rates recover what's like previously the best decoder for the 40-Tori code by Higgett and Breukman. So how does this look? Well, that's a lot. So let's first focus on the left-hand side. So on the top panel, we have the 3D-Tori code with Pauli noise, and on the bottom, we have the 40-Tori code with Pauli noise. What we see is that if we choose a window size of 1, that means we actually do single-shot decoding in the conventional sense, where we measure checks once and then decode immediately. We see that the threshold saturates for the 3D-Tori code at like just below 7.5%, whereas for the 40-Tori code, it's closer to 4.3, I think, in the end. But what we can do now is that via our like algebraic formulation, we thought, oh, actually you can increase the distance, time-lag distance, by choosing a bigger window size. And that's what we did. We chose 2 and 3. And we saw that the threshold immediately improves significantly for the 40-Tori code, going from this 4.3 later on to like something that's definitely above 6 for W equal to 3. And for the 3D-Tori code, it's approaching 10%. Now, because we have these analytical bounds on the time-lag distance, or this, not bounds, but like explicit expressions, we also now know that for the 40-Tori code and the 3D-Tori code, for the single-shot side of the 3D-Tori code at least, we don't have to repeat measurements d times. Well, we only have to repeat it L times. So L is this like linear distance of the 3D and 40-Tori codes, and not distance, linear size of the 3D-Tori code, whereas the distance is L square. But from our approach, which I will show on the next slide, basically it's like, oh, you don't need to repeat it L square times to get the optimal decoding. It's sufficient to do it L times. And this like dashed line is this is L. And for example, for the 3D-Tori code, which then becomes like a 40-Tori code with noisy measurements, we can actually recover something that's very close to like what is statistically optimal from a statistical physics mapping at I think it's like above 10%. And same for the 40-Tori code, we get to like almost 3%, which is the highest thresholds ever seen for 3D and 40-Tori codes. We have done the same thing for the Xanadu noise model, and I will spare you the details. But what we see is that if we just look at one side of the 3D-Tori code, we can get a threshold which is close to 8 dB of squeezing. For example, the surface code architecture that they're considering building now is just below 10 dB, so that's significantly better. Of course, this is not a true quantum error correcting code, as the other side has a much worse threshold, which is closer to 13 dB of squeezing. However, for the 40-Tori code, it's actually not so bad. We're ending up at roughly 10.3 dB of squeezing, which is not so far away from the 10 dB threshold for the surface code. And remind yourself that this code has a single-shot property, so there's like a space-time overhead that you might be able to gain from this. And yeah, as I mentioned, if we just look at these red lines, that reproduces exactly what Higgett and Breukman have done in 2023 for this single-stage decoding of codes with meta checks. So I mentioned that there's this notion of like lattice surgery, and that these time-lag correlations are important for lattice surgery. And now we get like the errors that flips these correlations analytically, so we can also compute what is the distance, so to say, of this time-lag logical correlation. And when we look at the 2D-Tori code, which is foliated with the distance delta repetition code, which is kind of like saying, okay, that's how many times we repeat these measurements in time, we find that the distance of the first homology group is the minimum of the code distance and the number of times we repeat it. So if we would repeat it only once, well, the code distance would be 1. So we should choose delta equal to like the code distance to like match these distances up, and then yeah, that's the code distance of the protocol. And that's kind of where this like folklore knowledge of like, oh, you should repeat stabilizer measurements on the order of d times basically comes from. And we now have like an analytical argument for it, why it's actually the case. However, if you do the same calculation for the 40-Tori code, because there's the presence of the meta checks, the results look a bit similar. So a bit different, namely, now you take the minimum of the code distance, which for the 40-Tori code would be L square. And then the other thing you should consider is the length of the repetition code and the square root of the distance. And here the square root of the distance pops up, basically because that's the distance of the meta check code for the 40-Tori code. So whatever you do for delta, if you don't consider delta to equal to 0, it's always going to be larger than square root of the distance or just the linear size L of the system. So that means even if you only do a single repetition of the stabilizer checks, if you make the code bigger, you will actually see that there's this threshold in doing this like time-lag stability experiments. Exactly. So we can see that this correlation surface can be preserved even if we repeat measurements only once. And this implies that there's like the existence of a fault-tolerant lattice surgery protocol with constant time overhead for auditory codes, basically anything that is like this 4D like length 4 chain complex with meta checks with non-trivial distance. And because our formalism allows us to like do these simulations so quickly, we also consider doing this, and for like numerical like decoding reasons, we stuck to the 3D toric code as an example and looked at the side that allows us to do single-shot lattice surgery or like a single-shot decoding. And we put the thing on we foliated the thing with a ring graph, so it's not a repetition code, but it's the repetition code on a ring. And that allows us to check for time-lag logical correlations, because else they're not really there, or we can't decode them. So what we see here is that if we repeat syndrome measurements only for W equal to 1, we see that there's a threshold, it's at roughly 6%. And if we scale the code up below threshold, the time-lag logical error rate reduces. If we make W larger, the threshold moves to larger error rates, and there's still a threshold. So unfortunately, I didn't show this here. I should have done this. But if you do the same experiment, for example, for the 2D surface code, there's no notion of a threshold. If you keep the window size, and that is like the number of measurements you perform before you decode, constant. So in the surface code, as Laura showed yesterday, to have like a kind of notion of a threshold, you have to increase the number of rounds that you repeat the syndrome measurement. Whereas here, we can do it a constant number of times, make the code larger, and still reduce the error rate of the code. I'm already coming to the end. I think I like rushed through this. Yeah. OK. So of course, we're not the only people who have thought about this. And there's been like previous work on fault-tolerant graph states and homology. And to some extent, it is actually funny because whenever I talk to people and tell them, oh yeah, foliation is just the hypergraph product with the CSS code and the repetition code, it's kind of like true by folklore. But to our knowledge, like nobody actually wrote it down, like computed the homology groups. And what we found was like, yeah, these nice properties about single-shot lattice surgery and so on. So we were heavily inspired by this paper by Newman, Leonardo de Castro, and Ken Brown, which is this like calculating fault-tolerant graph guides beyond foliation from crystal structures. Then there's also this chain complex formalism for foliation in the condensed metaphysics that people pointed out to us after we published our work, which is really focused on the condensed meta side and not so much on logical correlations. But also in other aspects, people are really like going away from the static QC point of view and going more to the channel picture that look at more like fault-tolerant protocols and how we can formalize them. There's some work by the PsiQuantum people. This is Lee from the magic state injection. There's Delphos and Petznick space-time codes, and also like Gottesman and his student Fu, who also looked at space-time codes in a slightly related formalism. So what did we do? Well, we introduced this fault zone complex, which allows us to like, it's a homological framework to analyze CSS-type fault-tolerant protocols. And it's this length 3 chain complex where the boundary maps are the detectors for Z errors, for X errors, and then there's this G matrix, which in the cluster state picture and the MBQC picture describe the biadjacency matrix of the cluster state. And what we also got is that as a special case, we could recover foliation as an algebraic formulation, which is just taking the hypergraph product code, the hypergraph product with the repetition code and the CSS code that we want to simulate, foliate. And this allowed us to like simplify frameworks for QC simulations significantly from what we did previously, at least. And with this like time-lag correlation and the distances of it, we could show that there's like a notion of single-shot lattice surgery if we have codes that have meta checks with non-trivial distance, and then there's this idea of potential space-time overhead reduction with 4D toric codes. Because if you want to achieve the same distance with a 2D toric code as with the 4D toric code, well, with a 2D toric code, if you want to do lattice surgery or like an identity block, it's going to be L by L by L, so it's going to be L cubed, and this block is going to have distance L. For a 4D toric code, which natively has distance L square, you actually only need L to the power of 5 halves, 2.5. So this is lower. So maybe this is going to be like useful in the future for reducing space-time overhead in general. So what do we want to do in the future? I already mentioned that I want to like hope that we can like push this fault complex away from phonological noise models to like analyze all like protocols in general. And something that we need to do is need to, like, even though we know how the fault complex can represent gauge-based quantum computation in the phonological noise model, the question is how can we generalize it to circuit-level noise? And there's some ideas that we already sketched in the paper that are related to the ideas of Lee. But then a question, as I'm like interested in decoding a lot, is like, no, now we know that there's like this additional structure in the space-time code that comes from taking the hypergraph product with the repetition code. Can we exploit this structure in the check matrices explicitly to improve decoders or to write specialized decoders that make use of that? Then I've made these examples very explicit for the repetition code, but all our homology results hold for any arbitrary linear code as an input and not just the repetition code. So it's interesting to explore other codes and what we get out of it. So then there's the question, okay, what would it mean operationally if we choose not a repetition code, but some general classical LDPC code? And then we ask ourselves, well, is this possibly a way to like recover filtering cluster states beyond foliation, as they were like introduced by Naomi Nickerson and Hector Bombin? And then, well, another question that goes in a similar direction is we restricted ourselves to taking the standard hypergraph product with the repetition code. But what happens if instead of using the hypergraph product, we take balanced or lifted product codes? Are we going to get better distances? Are we going to get more logic qubits? Are we going to like have some notion of like more qubits in the same space-time block? As we know that these constructions allow us to do like good static QEC codes. So what happens if we apply these constructions to like filter and protocols? And yeah, with that, thank you for listening to my talk.
Thanks, Timo, for a great talk. Do we have any questions?
Yeah, this is maybe common knowledge, I don't know, but with this, so with the 40 toric code example, you showed the time-like distance scale with the number of rounds times the square root of distance.
For the 40 toric code, you said?
Yeah.
Yeah.
So I just wanted to clarify, I guess, just conceptually here, because in later you were showing it when delta was constant, right? And the existence of the threshold. But I mean, just looking at that, wouldn't you want to set delta to be the square root of delta of dx as well?
Yeah.
In order to recover the.
That's like the best you could do, right? But then your like time overhead would scale with the size of the code, which maybe you don't want that. Then it's like maybe not a single shot code in the standard sense anymore, right?
Sure.
There's a question of what you want to do, right? I agree that if you do that, yeah, if you scale like the number of time steps with the size of the code, then you're going to get the best that you can achieve. And this is also going to give you this like increased space-time overhead or decreased space-time overhead. Yeah.
So you conjecture the existence of using these to like prove some single shot lattice surgery. What do you think is the biggest roadblock towards actually showing that?
I think for these like for like length 4 chain complexes, as long as like the meta checks have like non-trivial distance, I would argue that we have like shown evidence for like single shot lattice surgery with these type of codes. And I believe even if there's also like single shot codes that are just described by a length 2 chain complex. However, if they have like check redundancy, you can like construct meta-check matrices and check if they have some like distance that scales with the code family. So then you should also be okay. I think the only question in that respect that is really open is, well, there's some like or like single shot codes then that do not have redundant checks, for example, coming from like quantum tenor codes or quantum expander codes. And then there's really an open question that we cannot answer with our formalism. And it's possibly beyond our formalism, and they wouldn't know how to extend it to like check if these things have single shot lattice surgery.
About like going beyond the repetition code as the thing that you believe in.
Yeah.
Do you know of other constructions in the literature which might fit into this? Like I know there's like these fractal codes by like Yoshida, which kind of feel like that. Are those kind of things like you take the surface code and you foliate it with sort of a fractal, the classical code?
Yeah, I mean, we've thought about like fractal codes, but you could take convolutional codes, for example. So maybe they give you some like mix between like MBQC and convolutional quantum error correction. Yeah, so something that happens, for example, is that if you like take the service code and you foliate it with something that's not the repetition code, it immediately becomes non-matchable, basically. So you get more qubits for kind of like block, which is a reduced distance. So there's like these trade-offs. Yeah, the question is, what do you want, I think? And there's like, as like Sarah's talk on Monday evening said, like, well, there's lots of room we have to explore to find like what's the best code or best protocol to achieve the things that we want.
Any further questions for Timo?
You plotted the threshold as a function of rounds. Might be the slide before this.
Yeah.
Okay, so on that side, it looks like the threshold decreases with rounds, or it decreases on the.
Yeah, so like if you mean like, you mean like it goes up here and it goes down here? Yeah, so that's a like problem, so to say, because this is squeezing, and like the more squeezing you have in this GKP states, the like narrower the peaks of this comp state, and which is like, so in the infinite squeezing limit, it's like a perfect code, whereas in the zero squeezing limit, it's like pure noise. So like here, like lower is better, whereas here, higher is better. Does that explain now?